Hello everyone, and welcome to our second video in trying to solve some problems related to the empirical energy models. We were discussing FCC platinum using Lennard-Jones potential, and in the previous video, let me remind you, we calculated the single energy of just one atom, of the initial guess of the structure. Let me actually start a new folder here. Maybe I can call it optimization. And I will take a copy of this and put it in this folder. And the only change, remember in the previous video, there was the word single here. So the only change we will do in our starting calculation now is just to change this into opti, short for optimization. And then the rest of the file will be the same. And remember, we will start with an initial lattice constant of 3.8 angstrom. So let's see what's gonna happen after optimization. So save this. Now let's open the terminal, call gulp, software gulp version 6.2, binary gulp, platinum. Let's ask for an output called output.opti. And let's see, what do we have? Well, the first few lines are the same. Pretty much nothing has changed. So let's jump right away. Yeah, that was also the initial energy that we have seen in the previous video. But let's see what happened when the optimization starts. So notice that Gulb is telling you it's using the Newton-Raphson algorithm for optimization purposes. And it actually took two iterations after the initial guess. So that was the initial guess. And it took two iterations after that. And then the iterations stopped. Apparently, there is a criterion has been met, and then the optimization stopped. The final energy is minus 11.5, which is lesser than the initial energy. So we were really minimizing the energy of the structure. And Gulb acknowledged that optimization has been achieved. If you wonder what is the stopping criterion, it's something called the gradient norm, the vector, the norm of the gradient vector. And there is an internal criterion for its stopping when it's, so this one, the maximum gradient tolerance, if it is less than 0.001, then you should stop the optimization. In fact, at cycle number 2 or iteration number 2, it reached 0.0002, so it's less than the stopping criterion. That's why Gulp has stopped. Now, this is really the final energy of the structure, and we will use it, as you see in a couple of minutes. This is the final energy in kilojoule per mole, simple conversion. And now we see really something very interesting. The final lattice vectors, the optimized structure, has a lattice constant of 3.911 angstrom. We started with 3.8 as an initial guess, and upon optimization, we reach it to 3.9. In fact, this really answers the first question. Calculate the equilibrium lattice constant and total energy in electron volt for FCC platinum using the supplied Lennard-Jones potential. In fact, we answered both of them. So we can now write that the optimum lattice constant based on the Lennard-Jones potential is 3.911 angstrom. We will compare this in the later part of the question with experiments. And the total energy of the structure of the unit cell made of 4 atoms. Sorry, I'm opening something strange here. Yeah, the total energy of the structure is minus 11.525 electron volts. So that's the final energy of the structure. So really, we are done with the first part of the question. But let's see some other observations in the output file. One thing to notice is that the fractional coordinates didn't change. And this is something very useful about using fractional coordinates. Since the symmetry is still the same, we are talking about cubic FCC structure, the fractional coordinates of the atoms will remain the same as long as we maintain the same symmetry. The only thing that has changed is the length of the unit cell. So as long as you didn't change the symmetry, so the uh, 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 fractional coordinates will remain the same. That gives them some advantage. While if they were in Cartesian, you would have to change them, right? Whenever this number changes, because Cartesian really depends on the length of the simulation box. We will talk more about the advantages of fractional versus Cartesian in subsequent videos. Um, this is the new volume of the cell. Definitely it's larger than the initial because the cell has expanded. That's the final density. You can compare this with experiments as well. And that's the stress tensor. In fact, all of the components of the tensor are zero. Just keep opening this. So just um, to highlight what we have here, the stress is a tensor which can be represented by a 3 by 3 matrix where you have on the diagonal elements sigma xx, sigma yy, and sigma zz. And all of these are actually zeros, as you can see. So that means the structure is really optimized. So there are no forces on atoms and there are no stresses on the simulation box or in the unit cell. Meanwhile, the off-diagonal elements, they are actually symmetric. That's why we don't really need to report 9 elements. So you have sigma xy, which is exactly the same as sigma yx. You also have sigma xz, which is exactly the same as sigma zx. And finally, you have sigma yz, which is exactly the same as sigma zy. And these 3 off-diagonal elements, as you can see in the stress tensor, all of them are zeros as well. That's good. In terms of timing, definitely this is taking a little bit more time in comparison to the previous calculation. So yeah, so let's go now to the energy because we are ready to answer the second part of our problem here. So that's the total energy of the structure. So let's go to the statement of the second part. It says calculate the cohesive energy of platinum using the Lennard-Jones potential. So let's analyze this for a second. We want to calculate the cohesive energy. And if you remember what the concept of the cohesive energy, it is how much energy you gain or you lose when you bring atoms from far away to form a crystal, right? So that's, if you go back to the series of videos where we discussed cohesive energy, especially with regard to metals and metallic bonding and the embedded atom method, we said that the cohesive energy is the energy of the crystal made out of n atoms, so this is crystal, minus n times the energy of a single atom in vacuum or in a gas phase alone. And to make this quantity intensive in the language of thermodynamics, that's not depending on the size of the system, you need to normalize by dividing by the number of atoms. So in this problem, the energy of the crystal is the minus 11 something that we have just computed, minus 11,525 electron volt, minus I have 4 atoms in my simulation, times the energy of one atom in vacuum alone, described by Lennard-Jones potential, and then finally I will divide by 4 again. If I only know what is the value of the energy of a single atom in vacuum, I can plug it in here and get this number. And in fact, for pair potential, this is straightforward to think of. You don't really need, you don't really need to calculate it, although we can calculate it also as well. In fact, let me take a copy of this and go back and make another folder. I will call it single atom. And I will go here in that folder, paste this file, and I will change the name of the file. In fact, I will call it maybe atom.Lennard-Jones.in. And I just need the atom, single atom in vacuum, so I don't need to optimize any structure, so it's a single. What else do I want? I just need one atom, so there is no need for 3 atoms, so only one. I will make my simulation box very large to mimic the fact that it is really a single atom, so 15 by 15 by 15, for example. And there is a reason for why 15, and in fact 15 because I want any number larger than the cutoff of the potential, and this will be clear in a second when we discuss this further. Let me save this and ask Gulp to run this file. So we are calling Gulp 6.2 Gulp applied to our input, and let's ask for an output called out.atom, and it's done. We can actually go right away and see the answer, but before we do this, let's think a little bit. We can get the answer, of course, from the output file. Let's have some thinking. I have a big box. Let me make this 2-dimensional. I have a very big box whose length is 15 angstrom, and I have only one atom sitting here. Of course, under periodic boundary conditions, there is a repetition of this atom. So this cell is repeated in all directions, as you can imagine. In fact, this atom has an image here, image here, image here, and image everywhere. But since the cutoff of the potential is 12, right? In fact, you can draw some sort of circle in 2 dimensions or sphere in 3 dimensions. None of these images lie inside this sphere. In a sense, this atom does not see anything else. So it's not interacting with anything else. And because of this, its energy, if you look at Lennard-Jones expression, it's either you put 15 angstrom, but this is beyond the cutoff. If you remember, we said that if it's R less than R cut, use the Lennard-Jones expression. But if R is greater than R cut, then it's just 0. And that means that the energy of a single atom alone using pair potentials is 0. Let's confirm this. If we go back to the end of the file, yep, here it is. It is 0 as expected. Now, is this really something general? Is every interatomic potential or every energy model will give me a 0? The answer is no. If you do quantum mechanics, and this single atom has actually an internal structure, electrons, and these electrons interact together, then the energy of a single atom in vacuum will not be 0, right? There's a little bit more on this discussion, especially with the fact that there is no unique reference for energy, but let's defer this to a later part. For us in this exercise, it's as simple as if you go to the previous page, this number is 0. And then to get the cohesive energy, simply I need to, because this is 0, I need to divide the energy of the FCC crystal made out of 4 atoms divided by 4. And I think what I can do, let's close the terminal here. I can get it from the opti folder here if I open, not the input, if I open the output. Or in fact, let me show you some trick which you probably know already from your knowledge of Linux. I can grep the word energy from the output file, and in fact, yeah, it brings the energy for me, all the places where the energy word has been mentioned. And in fact, the energy, if you remember, it was minus 11.525. Let me take this on a calculator, put it and divide by 4, and yeah, that's the cohesive energy. We answered the second part of the question. So the cohesive energy of FCC platinum is minus 2.881 electron volt. By the way, some literature flips the sign of the convention, and in some literature you will find it in positive sign. but with the convention that we are adopting, which is, physically consistent with what we learn in physics usually. So it will always be negative, indicating a stable material, a stable crystal, thermodynamically stable or energetically stable crystal. Now, the last requirement we will cover in this video is part C, related to save, basically visualize the structure using VESTA and save an image in some format, for example, TIFF or any other format. So this is very simple, but I need to go to the optimized structure, which is actually here. Let's just go to the terminal. Thank you, Spider, for this help. Let's call VESTA. And if I open it, this is the optimized, that's the optimized FCC Platinum. And I can save this as an image from the file menu, export image, and I can, I can choose any format, for example, PNG, that's fine. And then I have to call this platinum.png, save. The scale, yeah, 1 is fine, as similar to what I see. Okay, and this was successful. Let's just confirm this for a second. Yep, here we go. That's the PNG image. So it was saved. And by the way, if you want to go to the folder where we did one atom, you remember, because also, not this one, the folder where we have a single atom, just to show you how does it look like, this single atom. In fact, let's open it here from VESTA. So go back to single atom, the CIF file. You see, yeah, that's a big simulation box. Its length is 15. You see here, 15, 15, 15, and 90, 90, 90. And the single atom is just repeated under periodic boundary conditions. That's what you see here. And if you remember the trick we said last time, if you want to get rid of this, simply make these X max, Y max, and Z max something like 0.99 and apply. Okay. And that's where we have a box where a single platinum atom exists and its energy with Lennard-Jones potential is 0. So we are done with the first 3 parts of this question. You'll stop here. See you in another video. We will continue this problem together. Thank you so much.